come in, you're bagging on physics. It's made so much harder on you when you forget the stuff that you already did, a month ago. It makes it harder on you. So at some point or another, I might have said that if there's an unbalanced force acting on an object, how much it accelerates will depend on its inertia. Have I said that before? Well, the unbalanced force is 2mg. The inertia of the system is 3m plus 2m, and that'll determine how much it accelerates. I mean, without drawing a free body diagram, that's all true. Now, yeah, you can get there another way, but it means that, 2/5 g is the acceleration of this system. Now, you can get there by doing a process, and I taught you about a process. I said, well, you could draw a free body diagram for each object in your system. And once you've drawn that free body diagram, you could kind of identify what direction you think the system will go, make out your positive direction. And then from there, you can build a Newton's second law equation for each object in your system. Once you've done that, you should ask yourself if the accelerations are the same values or not. Does the motion of one car correspond to the motion of the other block? I think in this one we can say yes. And once we can indicate that, we could bring these things together. Oops, I guess I can't. We can bring these things together. Use some manner of algebra to eliminate tension and be left with acceleration. Doesn't tell me what the tension is, but it gives me a manner in which I can find the acceleration. Once I have that, there's probably all number of places I could go to find the tension. So, forgive me, but you should be at least capable of doing this problem. We didn't have anything interesting here. It wasn't like this was in such a way that there was other forces acting in the system you had to deal with. So, this is very pedestrian. Very simple. This is well beneath you. So for those of you who couldn't do this, you understand why I could be frustrated. Because yesterday we added to this. We added mass to the pulley so that the pulley had inertia. If I add mass to the pulley, I change the dynamics of this equation. If the pulley is massive, then its inertia plays a role in the system. In fact, let's say that the pulley has a mass of 3m, the same mass as the car. And let's say that the pulley is a disc. We'll continue to say that there's no friction on the table. I'll keep it easy on you. But I indicated something yesterday towards the end of class that plays a role now. If the pulley has inertia, then its inertia is going to change the dynamic of the system. Do you think the system is going to accelerate faster because the pulley has inertia or slower because the pulley has inertia? I would agree. I think that there's going to be something added to this group of things here. There'll be more inertia in the system. I don't know how much more. Rotational inertia behaves differently than linear inertia. So we have to deal with the fact that this is rotational inertia. Also, the only way that pulley can actually accelerate is if there's an unbalanced torque acting on it. Now, you might not know why I'm saying that, but I notice that there are probably two forces acting on the pulley. Wouldn't you agree? Now, there's others. This thing that's holding the pulley probably has a force, and there's probably a downward force too. There's probably other forces, but these two are what's going to cause the pulley to turn. Wouldn't you agree? The only way they can cause the pulley to accelerate is if the torque is unbalanced, suggesting that this has got to be different than this. the tensions won't be the same on either side of the pulley. That was great first semester when our pulleys were massless, but now that our pulleys have mass, the tension is not the same everywhere in the string. I'm naming the tension on the table T3 to correspond to the 3M mass, and I'm naming the tension that's hanging to be T2 to correspond to the 2M mass, and I will now place a T3 here and a T2 here. That's going to change those relationships. But what you have to do now is you have to deal with the disc. I want you to come up with the torque arrangement for the disc. This is exactly what we did yesterday, except that with our example yesterday, there was only one torque acting on the disc. Today, you've got two. I found in first period I couldn't leave the class to just do this, that they had to do it with help. I'm afraid for this class that I probably have to do the same thing. And I got told things like, I don't understand my notes from yesterday. Sorry. So, net torque equals I alpha. That's a good start. And you should already know that torque is R times F times the sine of the angle between them. Again, we did this yesterday. Check your notes from yesterday. The difference is I think you have two torques. Now, some of you should be way past me. You should be like hurtling forwards. But I'm just looking around the room noticing that that's not the case for most of you. Is it clear to you that tension 2 is trying to cause the wheel to spin this way? And tension 3 is trying to get the wheel to spin that way? Based on what I've called positive in the problem, this seems like the positive direction to me. So I'm saying into the board is positive and out of the board is negative. You can check with your right-hand rule, but that's what I'm establishing. So into the board is positive for the torque. Now I'm just going to go ahead and erase that other arrow and start by looking at the torque arm. Looks like the radius of the pulley will be the torque arm for tension 2. So R times T 2 times the sine of 90 degrees. I'll remind you that no matter what pulley you have, if it's a circular pulley, the string's going to come off it as a tangent, and therefore the angle will be 90 degrees. Torque 3 is going to be negative because it's acting in the opposite direction, but its torque arm is still R. So R T3 sine 90 degrees. So if you haven't figured this out, when you're dealing with torque, you have a sub-step, right? It still behaves just like Newton's second law, but you have to assemble the torques first. Now, I would never write all of this out. I just write it in a straight line. But you might want to write them this way, so you make sure you cover all of the torques. I'm just trying to give you a framework, because you still have to sum the torques. That's what this means. Add up all the torques. When I add them up, I get RT2 minus RT3 equals I alpha. Well, that's it. That's what Newton's laws do. They produce relationships that you might be able to put together to solve a problem. I have produced my 3 relationships. Yep. Now, there's a difference here, And that is, in our prior example, I asked you to evaluate the accelerations and make sure the accelerations were related together. Well, we don't have a linear acceleration here. We have an angular acceleration. So with torque combined with force, you'll have to add an additional step here. After you've done your free body diagrams and you've assembled your torques and you've added the torques together and created a Newton's law equation, I'm not putting the steps on the board. We're past that, right? You guys are managing your own notes now. I have to decide whether I want to put this all in terms of the linear acceleration of the boxes or the angular acceleration of the pulley. And I have to do so by asking myself if the motion of the boxes is related to the spinning of the pulley. And I've tried to say this in all four of my classes that we have mechanics. My ones in the afternoon and the ones in the morning. And I get this like blank look on my face when I talk to you guys about it. But you're asking about how the pulley will turn as the boxes move. I have no easy way to deal with this except that if the pulley makes one rotation, can you imagine that a circumference worth of string will have passed by the pulley? I try to say it like that because you're supposed to know what the word circumference means. And I'm afraid that you don't know that that's the perimeter of the circle. And I'm afraid you don't know what perimeter means either. And I have good reason to believe those things, as we've seen so far today. But you're asking, or I'm asking, if how far the box moves, is it directly related to how far the pulley spins? You should ask that question, just as I'm saying it now. I know you're not writing it into your notes, so you'll just blow this off. But it's an important question, and one that I could manipulate if I wanted. I could produce a situation in which it's not obvious. So you should ask that question, does the motion of the boxes relate directly to how much the pulley spins? If it does, if they're connected, if the string moves across the pulley without slipping, then the accelerations are related by the radius. Now that doesn't fix the problem, but it does at least change one of the variables into one that's shared by all of them. You can either put all of it in terms of A or all of it in terms of alpha. Now this is getting overwhelming. So for those of you who are like looking at that board and your eyes are glossing over, how about this? T3 equals 3ma and 2mg minus T2 equals 2ma and RT2 minus RT3 equals I. I'm going to replace alpha with A over R. My three force equations. Now, you'll notice I still have I here. And that's because I didn't tell you the shape of the pulley. For all you know, it's a baseball that's been mounted to this thing, and I've passed the string over the top of the baseball. I don't know what it is. I didn't tell you. Leave it in terms of I for right now. Yeah.
You told us.
Did I? All right. Leave it in terms of I for right now. I have purpose. And I have to hurry for this purpose because the bell's going to ring. As a hint, collect your R's. I divided both sides by R. But then group the R with the moment of inertia. If you know your shape, that's fine. Plug it in whenever you want. If you don't know your shape, do you realize that every one of the circular shapes has R squared in it? If you group the R with the moment of inertia, you have grouped everything that has to do with the shape of the object in one place. Now, I did say it was a disk, So I'm going to plug in disk, but remember, the disk has mass of 3m. A mistake you are likely to make, and I'm likely to exaggerate on purpose. Right? Don't just put m in here. These m's represent the mass of the object, but the mass of your object was 3m. If done correctly, oftentimes, the radius will cancel out. So now put it together. You'll have 3 equations, but all of your tensions should cancel out. And you'll be left with 2mg. I'm sorry, I didn't put the m there, and I should have. So I know you should leave, but you should write this down before you do so, because you're not going to watch the video. No one should watch the video. Is it clear to you that there's more inertia now? We only had 2 of them before, but you notice we have more things here. All right, look.